All right, so in the following example, I want to look at how do you assess reactions in solutions. So essentially, you have two separate solutions and you mix them. Then what do you need to do to assess whether or not the reaction takes place, whether or not you're just mixing two solutions, and of course, then what happens subsequently. So in this specific example, we're told we need to determine the molarities of all ions present in a solution made by adding a certain amount of barium hydroxide with a certain amount of hydrochloric acid. And then thereafter, we need to determine the pH of the resulting solution after the reaction has taken place. Right. So let's first think about what's happening here. We're taking two beakers. The one has barium hydroxide in it. The other one has hydrochloric acid in it. Solutions of those, right? So for this one, we're told we have a volume of 1.50 times 10 to the 2 milliliter. That's commonly known as 150 milliliter. And for this one, also for that, we're also given the concentration of the barium hydroxide as 2.00 times 10 to the negative 2 molar. For the hydrochloric acid, we're given the volume, which is 100 milliliter. And we're given the concentration of the hydrochloric acid to be 5.00 times 10 to the negative 2 molar. Okay, so that's our situation. First, we need to determine the molarities of all the ions present as a resultant of these solutions. So how do we determine what's going to happen? Well, the first thing is, are we just mixing two solutions, making up a solution with a larger volume, or do we have a reaction? So like a precipitation reaction, a gas-forming reaction, an acid-base reaction, a redox reaction. What are the possibilities? Now, from your knowledge of what you've studied, you should know that barium hydroxide is a strong base. Oxides of the metals of group 1 and 2 are strong bases, or hydroxides of groups 1 and 2, as well as hydrogen or hydrochloric acid is quite a strong acid, commonly known. So from that, you should realize that this is an acid-base reaction. It's a strong acid with a strong base. So that is also important. So that means our reaction is barium hydroxide, which is in solution, reacting with HCl, also in solution, to give barium chloride, which is an aqueous salt, plus water, which is of course a liquid. Now you'll see I've already balanced the reaction, so there's a 2 in front of the HCl and a 2 in front of the water. So that's something you can do in your own time, but it is balanced. So what do we need to look at to determine what is actually happening at the end? So what do we have at the start? We're given volume and concentrations for the two solutions. And we know that these two solutions, the compounds in the solution, will want to react. And we know we cannot compare masses, volumes, concentrations of species. The only thing that we can ever compare is the number of mole. So let's start by calculating the number of mole of each of these species. So the amount of mole of barium hydroxide that we are adding will be equal to the volume multiplied by the concentration. So it will be the concentration of the barium hydroxide multiplied by the volume of the barium hydroxide. So that is 2.00 times 10 to the negative 2 mole per liter. And that is multiplied by 150 times 10 to the negative 3 liter. So I've just converted the milliliter to liter. The liters cancel, and we should then get 3.00 times 10 to the negative 3 mole. Right. That's our first step. So now we know how many moles of barium hydroxide we have. The next question is, how many moles of hydrochloric acid do we have? Well, so again, it's the concentration of the solution of hydrochloric acid multiplied by the volume of the solution of hydrochloric acid. And what are those? It's 100 milliliter and 5 times negative 2. So 5.00 times 10 to the negative 2 mole per liter multiplied by 100 milliliter. So 100 milliliter is, of course, 100 times 10 to the negative 3 liter. Okay, and this one is 50 times 0.1, so it is 5.00 times 10 to the negative 3 mole. Okay, now we know how much of each we are mixing in reality. But from the chemical equation, we know what their ideal ratio will be. So we know 1 barium hydroxide, 1 mole of barium hydroxide, would ideally like to react with 2 mole of hydrochloric acid. So let's plug one of these in. So for example, we know we have 3 mole, or 3 times times 10 to the negative 3 mole of barium hydroxide would like to react with twice that much HCl. So it will react twice that, so it will then be 6.00 times 10 to the negative 3 mole HCl. Right, so for all the barium hydroxide to react, we need at least 6 times 10 to the negative 3 mole HCl. But how much HCl do we have? We only have 5 times 10 to the negative 3 mole, whereas we will require 6. And that per implication then means that HCl is our limiting reagent. So we then write explicitly, therefore HCl is the limiting reagent. And what does that mean? It means all the hydrochloric acid will be used up, and then there will still remain some barium hydroxide. So we need to determine what that is. So let's again, we look at our ratio. So it's barium hydroxide, so 1 barium hydroxide will react with 2 HCl. So that means 5.00 times 10 to the negative 3 mole HCl will react with half that much barium hydroxide. So we'll react that divided by 2, so 2.50 times 10 to the negative 3 mole barium hydroxide. Right. And we can see, so how much barium hydroxide do we have? We have 3 times 10 to the negative 3. We're only using 2.5 to the negative 3, so that means there's going to be 0.5 times 10 to the negative 3 barium hydroxide, mole barium hydroxide still left in reaction. Yeah. Okay, so importantly, that's what we figured out. So we figured out, therefore, there will be, so let's just write it out nicely. It's going to be 3.00 times 10 to the negative 3 mole minus 2.50 times 10 to the negative 3 mole barium hydroxide. Now let's first work it out. Is equal to 0.50 times 10 to the negative 3 mole barium hydroxide left. Left after reaction. Okay, so now let's look at our equation again. So there's some barium hydroxide left. All the HCl has reacted. And what has it reacted to form? It has formed barium chloride and water. Okay, so we're asked for the molarities of all the ions present after the solution has been made up. So the ions that will be present is barium, chlorine, hydroxide. Okay, and water is not an ion, so you don't have to worry about that. Okay, to calculate the concentration of anything, we of course need the number of moles and the volume of the total solution. So the volume of the total solution is equal to, we need to add the two volumes. So it's 150 plus 100 milliliters, so that's 250 milliliter, right? Or 250 times 10 to the negative 3 liter. So that's our volume of our total solution. How many moles of, let's first do the easiest one, or the easier one. What are the number of moles of hydroxide? So what do we say is all left? So there's barium hydroxide, so let's say left after reaction. Left after the reaction, there's some barium hydroxide left. There's barium chloride that has formed, and there's water. Okay, all the HCl has reacted. Barium chloride is an aqueous, or is a base, so it will split into barium 2 plus 2 hydroxide ions. Barium chloride is a soluble salt, so it means it will split into barium 2 plus 2 Cl minus ions. And water is not an ion, so it's irrelevant. It's just the solvent. We've made more solvent. Okay. Interesting argument there. We made more water, so doesn't the volume increase? That's a good question. Okay. So what do we have at the end of the day? What are the ions present after reaction? So it's definitely bariums. There's hydroxides, hydroxyls, and chlorine ions. So we need to calculate the number of moles of each of these species that are left, and then we need to calculate their concentration. So let's start with the easier ones. So let's start with the number of mole of Cl minus that has been produced. If we look at our equation, we see that, of course, there cannot be more Cl on the right-hand side than there is on the left-hand side. And we've already calculated the number of mole of HCl. So meaning HCl is 1 hydrogen for every 1 chlorine. So if the number of moles of HCl is 5 times 10 to the negative 3 mole, it means the number of mole of chlorines that would have formed on the right-hand side would just be, well, twice times 5.00 times 10 to the negative 3 mole. This is also colloquially known as 1.00 times 10 to the negative 2 mole. Right. How much hydroxide is left over? What's the number of mole of hydroxide? Well, the only information about the hydroxide that we have is that we had so much barium hydroxide left, and that can be the only source of hydroxide after the reaction. But we know barium to hydroxide is a 1:2 ratio. So it splits into 1:2. So in other words, for every 1 barium hydroxide there needs to be twice as much hydroxide and ions. In other words, number of moles of hydroxide will also be twice the number of moles, so 0.500 times 10 to the negative 3 mole. And that gives us 1.00 times 10 to the negative 3 mole hydroxide and ions left after reaction. And then we have the barium. But barium has 2 sources in this case. So it's the number of moles of barium 2 plus is equal to the number of moles of barium 2 plus, let's call it left, plus the number of moles of barium 2 plus formed. And the formed refers to the amount of barium now trapped in the chlorine, or the BaCl2. And that should actually just add up to its original value. But anyway, for the purposes of this, it means there's 0.500 times 10 to the negative 3 mole plus the amount of barium chloride that could have formed is 1:1 to the amount of barium hydroxide at the beginning, but it's also 2:1 to the amount of HCl. So in other words, it is HCl divided by 2 will give us the amount of barium chloride. So because HCl is our limiting reagent, so it means barium is then 2.500 times 10 to the negative 3 mole. That comes from the hydroxide, or the HCl. And then, oh my goodness, we're left over with, that is what we started with. So there is 3 times 10 to the negative 3.00 times 10 to the negative 3 mole barium 2 plus in solution. And why is that? Why is the total amount of chlorine equal to the same amount that it's on the left-hand side. So if you had to calculate the amount of chlorine on the left-hand side, you would have said, well, that is the concentration of HCl times 2. And if you take that, or the amount and the number of moles, then you get 1 times 10 to the negative 2. And if you want to determine the amount of barium, we saw that it is now just equal to the initial amount of barium hydroxide, so the same number of moles. Why is that? Well, it's because, of course, your net ionic equation in this reaction is that OH minus plus H plus forms water. That is, in principle, what is happening here. But you have to balance it, so you'll write it as 2, 2, 2, whatever. So your net ionic equation is only the hydroxide, the hydrogen, and the water really plays a role in this. Both barium and chlorine are spectator anions. In other words, their number of moles should not change because they're not really part of anything. The only thing that should change is the hydroxide because it has lost a certain amount of it during the reaction. So it doesn't have the same amount on the left-hand side as it has on the right-hand side because there's no of it on the right-hand side. So there's only a bit of it left because it's the excess reagent. So you could have done it like that as well. But this is the systematic way that you can do it. So now that you have the number of moles, we just need to calculate the concentrations. So the concentration of Cl minus, otherwise written as brackets Cl minus, is then equal to the number of moles of Cl minus divided by the volume, and the total volume is 250. So we have 0.1.00 times 10 to the negative 2 mole divided by 250 times 10 to the negative 3 liter. And then you should find 10 divided by 250 is 1 over 25. You should then get 2.00 times 10 to the negative 2 molar. Concentration of, which one is this, of hydroxide is then going to be our 1.3, so we cancelled that. 1 over 250 is equal to 4.00 times 10 to the negative 3 molar. And the barium will be its initial concentration, so it's barium 2 plus. And that is equal to 1.2 times 10 to the negative 2 molar. And let me just check that everything makes sense. Yeah, happy with that. 3 times that. Good. Okay. So that is the concentration of the species that we wanted to get to. But what are we actually asked? Or the next thing that we're asked? We're asked to determine the pH of the resulting solution after the reaction has taken place. So how do we calculate pH? Well, we normally say pH is equal to minus the log of the concentration of hydronium, right? Or minus the log of the concentration of H plus. But the question here is there any H plus left that you know of? No. All the hydrogen chloride has reacted. So there's only OH minus actually left. So how can we use that information to calculate the pH? Well, it turns out, so if you have a pH, right, then it means you have to have a pOH as well. So there is a similar expression where you can say pOH is equal to minus the log of the concentration of OH minus. You see the similarity, pH and POH, and you have hydronium and hydroxide. All right, and there is a special relationship between pH and POH. So the pH scale goes until 14, and these two must always sum to 14. In other words, if we calculate the POH, we calculated the concentration of hydroxide just here. So we can calculate the POH minus log of the concentration of hydroxide. So that's 4.00 times 10 to the negative 3. Yeah. And then it means that it's 10, 40, okay. You will get a value of 2.39 and some numbers. So that means the pH is equal to 14 minus the POH, and that is equal to 11.60, 601, I think. Three significant figures. Yeah, three significant figures. So 0.62 is the pH. All right. So this last part is important because it introduces a new way to calculate pH, which is a different way to get it to it from the hydroxide. You can, in principle, get it from other methods. And this one was interesting to see how you could have actually already written down the spectator ion concentration just from calculating the number of moles of them present at the beginning and divided by the final volume, because that's in principle what it is. The only thing that changes is the things that, of course, react, and the things in the net ionic equation. So I went a long way around so that you can see that is what happens at the end, versus saying, oh, this is something we know that happens, so we can just do that immediately. Okay. I hope this is useful in your endeavors in life, and I'll see you in the next video. Thank you for watching.